Prior to joining Chicago, he received his PhD in applied math from Case Western Reserve University in 2020. Alex works in a variety of interesting areas, broadly studying the structure of networks that arise in a variety of disciplines, including biophysics, ecology, neuroscience, and in competitive systems. He draws on tools from discrete topology, non-equilibrium thermodynamics, and functional form game theory to study the interplay of structure and dynamics in these systems. Today, we are excited and fortunate to hear from him on the topic of strategic feature extraction and low-dimensional representation of games. Thanks, Alex. Take it away.
Okay, thank you very much. So thank you, Jamie, and thank you for the invitation to talk in this seminar. I'd like to start by thanking my collaborators on this work. So this is joint work inspired by a collaboration with LAIC, which is Lockheed Martin's AI and Computing Center. And then some of this work is sort of joint work I've done with some master's students here at the University of Chicago. Their names are not on this slide. They should be on this slide. Those are Zilai C, Yukon Liu, and Patrick have all sort of contributed to this general project. So without any further ado, let's introduce the topic. So motivation. Our goal today will be to construct a latent space representation of generic two-player zero-sum games that satisfies some desirable criteria. And I'll have a whole list of criteria here. First, we would like to represent our generic game as a combination of simpler canonical games that are sort of easy to understand and represent. We would like these canonical games to be visualizable so that coordinates in the latent space have intrinsic strategic meaning, and that if we can sort of plot agents in this latent space, then their relations, their positional relations within the space carry strategic consequences. That's important because essentially, in some sense, we're translating the structure of a game of advantage relationships, payout relationships, utility, whatever you like, into geometry in the latent space. We would like this construction to allow some sort of model or dimension reduction, and that's to produce some measure of the complexity of a game. And again, it's sort of as usual when you're working with a latent space, we'd like in some sense to go from a high dimensional space to a low dimensional space so that it's easier to work with and represent our agents. We would like this space to be meaningful in some sense. I mean, so this is going back to what I was emphasizing on the visualizable point. If we want the geometry of the space to carry meaning, if we want coordinates or position in the space to carry strategic meaning, then in some sense, we would like the space to represent strategic features of the game. And this is analogous to identifying feature vectors in sort of, you think, standard embedding techniques. The idea here is that instead of identifying feature vectors, we'll be identifying strategic features. And because of the type of canonical games we use, these are essentially trade-offs. These represent decision dilemmas that the players have to face. This approach will allow game classification and construction and will allow us to interpolate beyond empirical data. So hopefully I don't need to justify the relevance of game theory in general, right? You could think that this type of approach might be relevant to a variety of competitive systems across the natural sciences. So maybe in biology, you're thinking ecology or evolution, within sports analytics, social choice, global politics, war and wargaming, business and economics, and so on. Everything I'll say today will also be applicable to general decision tasks where your data is available as pairwise preferences, and so you can view the decision task as a two-player zero-sum game. This is also relevant to topics in machine learning. You can think reinforcement learning is very hot. Reinforcement learning uses games as a test bed for developing learning techniques. All right. The methods that we will be discussing today are inspired by some work out of Google DeepMind that's cited here, these citations 1, 2, 3. This is work from David Balduzzi while he was a member of Google DeepMind. And what I will be doing today is illustrating, extending, and developing a formal approximation theory for the methods introduced by that team at Google DeepMind sort of in 2018 and 2019. Okay, so without further ado, let's specify our sort of problem space. We will be considering a particular type of game. These are what are called functional form games. A functional form game is a two-player, zero-sum game where your notion of payout or performance or utility is a function of your agent attributes. You can think this is very relevant in empirical settings like maybe biology or in sports where attributes could be physiological characteristics of your agents or statistics describing the way your agents play. So maybe you collect baseball statistics. In order to specify a functional form game, then, we need a list of attributes or space of possible agent attributes. We'll call this omega. This we'll think about as a subset of the reals where T here is the number of traits or attributes I consider. You could consider this a subset of the complex numbers. This could be ordinal valued, but most of what I'll focus on today are examples where omega is some continuous, maybe compact or convex subset of RT. That's not required, but that's sort of the image I've kept in my mind for most of the work. Then, given a space of possible attributes which parameterize your agents, then there has to be some function which accepts your description of your agents, that is attributes, so description of agent 1, description of agent 2, and returns some measure of the advantage that agent 1 possesses over agent 2. We'll assume that we're looking at two-player zero-sum symmetric games, in which case this function that maps from pairs of traits to the real numbers has to satisfy the sort of fairness criteria that the advantage x possesses over y is the disadvantage y possesses relative to x. And you can think that really these functional form games, this is just equivalent to a generic zero-sum, let's just say symmetric game on a possibly continuous strategy space. Okay, now the other key restriction that's important for this work is the restriction to empirical game theory, that is the study of a game through observed or sampled game play. And really the conceptual difference between empirical game theory and sort of classical game theory is that empirical game theory is deeply concerned about the population of agents who actually play the game, as opposed to maybe theoretically finding the optimal agent or finding equilibria. You could think that empirical game theory studies a game as experienced by a real population or some specified population, as opposed to studying idealized play with respect to that game. In this setting, our data often comes in the form of some sort of tournament. That is, we have a competitive system containing finitely many, maybe sampled agents. And we'll be interested in collecting interactions between agents and then trying to infer things about this underlying function based on those interactions.
我也不知道，感觉他挺强的感觉。
Maybe, sorry, was that a question or just somebody needs to mute their chat?
I think
Okay.
we're good now, Alex.
Yeah, thank you. So here, when we're considering empirical game theory, really we're thinking that we are either restricting our attention to finite samples of this function f, where we don't actually know the underlying function, but we can sample it, or that we have some underlying distribution of agents, we could call that pi over omega, which describes sort of an idealization of your population. All right, and again, both of these setups apply to decision tasks as well as to sort of a game theory setting. Okay, now we can start by posing some different examples of functional form games. These we can think of sort of as canonical test cases. The simplest class of games you can think of sort of transitive or hierarchical games. These are games where f of x comma y is r of x minus r of y, where r is some rating function that takes the attributes of an agent and returns a real number. You could think really what this is saying is that each agent can be assigned some innate quality that's independent of their opponent, and the game is just a comparison of that quality. Another class of game would be linear games. So you can think f of x, y is maybe some vector v dot x minus y. And actually all linear games are transitive games. You just define r of x to be v dot x. Another broader class of games are translationally symmetric games. This would be f of x, y is some odd function g applied to the difference of x and y. So this is a game where the absolute trait values of the agents don't matter, but the difference determines their relative performance. And these have sort of special features. For example, you could look at what we'll call the sine game. We just set f of x, y to be like some amplitude times sine of omega x minus y. And this is a nice test case for the embedding that will come later. Now let's push to a little bit more generic games. So linear games, these are strictly transitive. The next highest order polynomial game will be a quadratic game. And you could write a generic quadratic game in this form where you sort of have this list of a linear term and then some set of quadratic forms around a pair of matrices where these matrices have specific symmetries. In particular, A is symmetric and B is skew symmetric. This family of quadratic games, this includes all zero-sum bimatrix games. Really, you could think this includes all normal form games where x and y represent policies or sort of probabilities of choosing a particular pure strategy. And then pushing even more generic, you could write down a generic polynomial game here. This is f of x comma y will be some sum over different orders of multi-indices that sum to that order of some difference of polynomial terms in terms of x and y. And this tensor C has certain enforced symmetries that come from the skew symmetry of f. Now, certainly most functional form games in real life would not fall into one of these categories, but I'll use these different categories as examples of games that we can explicitly embed and as test cases to help motivate a more general theory when we think about generic functions f that we don't have control over and aren't defined in this nice fashion. Right, so now what we said was we wanted a canonical sort of simple game that we could combine to express generic games. And the game that we'll use here is what's called a disk game. This is, you can think of essentially a two-dimensional extension of rock, paper, scissors. This is a functional form game in R2, where f of xy is just defined as the cross product between x and y. And you can think in some sense this models a trade-off between two traits or two attributes, that the optimal response to, say, an agent here on the x-axis is given by picking an agent on the y-axis, who's maximally exploited by reflecting your x-axis, so is maximally exploited by moving 90 degrees around the origin, who is again optimally exploited by moving 90 degrees around the origin, who is optimally exploited by the agent that I started with. So you can think that in some sense, if you look at just the 4 points on the axes, this is like a 4-point rock, paper, scissors cycle, except of course, the same thing is true everywhere in the space. And so this is sort of a continuous extension of rock, paper, scissors. This game is particularly nice because the cross product is a deeply geometric product, which means things like, say, the value of this cross product can be inferred directly from geometry in the space where the agents live, right? So for example, this value, like x cross y, that'll be proportional to the signed area of a triangle given the origin and the position of the two agents in the space. Or you could think about assigning a circulating vector field behind the space, and then the value of the comparison, f of xy between 2 points x and y, will be the line integral against that vector field. So you can think whenever you see this vector field, that's just providing sort of a visual cue to think that advantage in this game is going to flow downstream around the origin. All right. Now, our embedding goal is to represent a generic functional form game as a linear combination of these disk games. To do this, we need two pieces. We're going to need some sort of generically nonlinear piece, which performs the mapping into the disk game space. This is our embedding. We're looking for some potentially nonlinear change of coordinates, which we'll call the embedding map y, mapping from omega into r to the 2d, which we'll think about as a sequence of d planar embeddings, where like yk is the mapping from omega into r2. I mean, you can think yk has elements here, y2k minus 1 and y2k. And you can think for the kth planar embedding, this is like your horizontal coordinate, and this is your vertical coordinate. Then we'd like to equip each planar embedding with that disk game dynamic. You can think there's a deep analogy here to things like reproducing kernel Hilbert spaces, where you're looking for some generic embedding into a lower dimensional Euclidean space, and then you're replacing some sort of symmetric kernel in some sense with just the inner product in that space. Here we're doing effectively the same thing. We're starting with some generic functional form game, and we're trying to embed our original trait space, so positions as described by our original parameterization of the agents, into some lower dimensional Euclidean space that we break up into the sequence of planes, and we apply a cross product on each plane. You can think schematically what this is doing. We're saying given f and omega, we try to find y so that each agent is assigned a point in a sequence of these planes, and then the competitive relationship or performance or advantage that one agent possesses over another is given by the cross product of their coordinates summed up across the planes. And so then we're representing our generic function f as a linear combination of embeddings into disk games, with the idea that each of the disk games is deeply geometric and each disk game is two-dimensional. So we can visualize performance relations via projection or mapping into each of these individual disk games in slices of this latent space. Okay, so that's our goal. Now let's talk about what exists. So what exists is principal trade-off analysis, which is a method for performing this type of embedding when we're restricted to point-wise samples of our function f. So let's talk a little bit about point-wise embeddings. So empirically, suppose we'd sampled a collection of agents. So we have an ensemble of agents. You can think about this as a population. This is just a list of agents from 1 up to capital N. Then at the most sort of expensive, most information-rich version of this approach, we could try to evaluate performance between all pairs. That is, we build some matrix where the ij entry of the matrix is the value of that sort of utility function, that payout function f, evaluated between agents I and agents j. Because we assumed that our game had this skew symmetry, this matrix will also be skew symmetric. Note, we don't actually need to use complete matrices here. Obviously, complete sampling would be very expensive. In practice, you can often get away with incomplete sampling if you apply a sufficiently stable matrix completion technique. And of course, there's all sorts of challenges numerically and statistically with ensuring that that matrix completion is robust to your choice of samples and to errors in the evaluated points here. But for now, let's just imagine that we were able to either evaluate F everywhere, or we were able to complete some incomplete data set to get a good guess of what this matrix would look like. Then what we're looking for from the pointwise perspective is a mapping of the individual agents, so that each individual sampled agent, which is just a list of points in your original trait space, to points in this sequence of planes, such that the sum of cross products between these embedded individuals recovers this matrix. And this is basically just a matrix decomposition. What we're doing is we're trying to find a matrix of embedding coordinates, Y, that assigns each agent a specific embedding coordinate in R2D, so that this particular sort of funny matrix product, where I take Y, cross product Y in each 2x2 block, and I sum it up, recovers this skew symmetric matrix. And if you've played with the spectrum of skew symmetric matrices, you might recognize that this is exactly what's called the real SCHUR form of this skew symmetric matrix. It's basically the SVD of the matrix rearranged, or the eigenvalue decomposition of this matrix rearranged to be, instead of representing the spectrum in terms of imaginary and complex numbers, we represent the spectrum purely with real numbers, but we have to introduce some little sort of rotation matrices, and those rotation matrices enter in through this cross product. Okay. As a result of the existence of the SCHUR real form, we can guarantee that this is always possible. So upon restriction to a finite point set, any functional form game admits a disk game embedding such that performance between the traits in the point set is a linear combination of disk games applied to the pointwise embeddings, which means that this is possible very generically, at least if we're limited to pointwise data. Right. Now, again, the key tool here is this particular matrix decomposition. So let's remind ourselves of this decomposition. If we're given a real skew symmetric finite matrix A, this admits a SCHUR real form. You can write A is like QU, Q transpose, where Q is real valued M by N and orthonormal, and U is block diagonal, where the diagonal blocks are 2x2 and are given by little 90-degree rotation matrices. These scalars here, these omegas, these are related to the eigenvalues of the matrix A. These are, in effect, the singular values of the matrix, or the magnitude of the eigenvalues of the matrix A. It's the imaginary part of each eigenvalue. And the columns of Q, these are associated with the singular vectors or the eigenvectors of the matrix. These are essentially scaled versions of the real part of the eigenvectors and the imaginary part of the eigenvectors. All right, so if you can perform sort of any standard spectral decomposition of this matrix, you can perform this SCHUR real form, and truncation of this SCHUR real form is equivalent to truncation of a standard like singular value decomposition. Right? It follows that truncation of this particular product, so say I cut Q off after a certain number of columns, maybe D columns, that will produce the best rank D approximation to A in Frobenius norm, because that's the same as truncating the singular value decomposition after D terms, or up to rank D. Okay, so that's our matrix decomposition tool. Applied to this embedding problem, this is a somewhat powerful thing. In a sense, this gives us a method analogous to principal component analysis, but specialized to the structure of trying to isolate strategic trade-offs, right? Just like PCA, each of the embedding vectors are orthogonal to one another. So they represent, and here I put like independent in quotes, cyclic modes or trade-offs in the game. You can think again, right? Each of these disk games represent some sort of continuous rock, paper, scissors trade-off. So if I can embed points and those points land around the origin, then I have a cycle of advantage relationships around that origin. And that will represent some source of sort of cyclic relationships in the games. We can think about that as some strategic trade-off. Right. Now, here I said independent in quotes because, of course, orthogonality is not the same thing as statistical independence. This is really saying that the coordinates assigned to each agent are uncorrelated if you sampled the agent at random. In addition, the embeddings form a low-rank optimal sequence. This follows from the idea that truncation of the SCHUR real form is the same as truncation of the singular value decomposition, which means that I can cut off the sequence of embeddings after D terms, and I'm left with the best rank D approximation to the original performance function. You can think this is in Frobenius norm, so it's equivalent to saying that I've captured as much of the variance in performance as I can up to a certain number of embeddings. Moreover, the importance of each embedding in this series is quantified by the corresponding eigenvalue in the usual fashion. And since performance in a disk game comes from a cross product and is proportional to area, this eigenvalue is actually related in some sense to the area of the scatter cloud seen in each disk game. So we can visualize directly sort of the importance of each disk game just by the spread, really the total variance of the set of points as they are embedded in the disk game. Right, so that's the sort of general idea pointwise. Let's test this on some example cases. So let's try to build some intuition by running some simple games. Here are an example, or really 3 different examples of this sort of disk game embedding for some simple synthetic games that have nice mathematical symmetries. Here, this game on the left, this is a Gaussian sort of extension of rock, paper, scissors. This is a different way of extending rock, paper, scissors to a plane. And we see we get these beautiful, really clearly defined shapes. Right? This would be an example where, again, embedding has translated some underlying set of performance relationships into some characteristic geometries in the embedding space. Right? And really, that's where all the interest in this approach lies, in the idea that we are translating structure of a function into geometry in a latent space. Right? So, for example, we see here that in some sense, without knowing what this actual functional form is, we can infer things about its structure by looking at the embedding. Like here, we have exactly a rock, paper, scissors cycle between 3 different types, these different arms. Each arm is sort of equally an optimal counter to the arm that precedes it. And we sort of have an intensity or degree of intensity to which agents within an arm are involved in that cycle, because the farther you move out on this arm, the larger the cross product with the arm that follows it. Right? And then here, this is also some different notion of sort of a 3-point cycle, but this is sort of more continuous, where we can move continuously between our 3 different types. This would be different examples. So these examples, these are some sort of randomized multi-criteria decision-making problems where we generate different random matrices related to some sort of pairwise preference. And these are designed in different ways so that their bulk structure, as seen through the embedding, have different numbers of cyclic modes in them, which can be counted by counting the number of corners of these polygons. This example here is another sort of synthetically constructed example where, again, we're looking at pairwise preference, where we take a population of individuals and we have them rank some objects or some candidates, and we break the population of individuals into different random subsets, where the subsets' relative preference orders are all cyclic permutations of each other. And the result is we see these different sort of circular segments, right, little arc segments, that in some sense are arising from these different population segments. Now, some of what I would like to do with this talk is to really start to focus on the functional theory behind this pointwise approach that justifies the beautifully geometric shapes we get out when we plug in synthetic games. Right? We'd like to be able to interpret these structures, right? What do these semicircles mean? Now, some other examples, you could also just test different sort of randomized games. So this is a figure pulled from, again, sort of Google DeepMind. This is the Spalduzzi paper here, with different randomized matrices that have sort of different overall structures. This is a game that's almost transitive, so it's almost just a comparison of rating. And we see that the disk game becomes essentially a set of points on a curve or a line. We'll be able to prove that this is necessarily true if a game is transitive. This is a game that's almost cyclic and corresponds to some sort of essentially one continuous rock, paper, scissors cycle where all agents are equally involved in the trade-off. There's no difference in degree of involvement because there's no way of moving inwards in this set, right? This is a curve enclosing the origin. Maybe another example, we could look at like rock, paper, scissors with more than one type. So again, this is to help build intuition. We consider, for example, rock, paper, scissors +2, where we have 5 different types. This is like rock, paper, scissors, lizard, Spock. This is a normal form game. The projections here are embeddings of the simplex. Here we've generated our data by running a training algorithm on agents. So this is run using self-play. And what we see is that these embeddings form approximately regular polygons that reflect the symmetries of the underlying game. And these 2 polygons, these correspond to the fact that RPS +2, this rock, paper, scissors, lizard, Spock, essentially it's a normal form game. So my embedding is some linear projection of the simplex of policies, which is why these end up being polygons. The polygons are regular because of the symmetry of the underlying construction. And there are 2 different interlocking symmetric cycles in RPS +2. And those are represented by taking the same polygon. Here we have both of these are circumscribed inside a regular pentagon corresponding to the 5 different types. and moving around that pentagon, skipping a different number of corners each time. And these two sets of cycles are sort of symmetric and interlocked in a way that's defined by the specific functional form, and that you could read off of this type of plot. Right, now, this also works for more interesting games. So for example, let's take Pokemon. Here we are considering Pokemon, sort of the video game Pokemon. There are different types or classes of Pokemon that can compete with one another. And what we've done is we've taken these different types of Pokemon, we've trained an AI to play as that Pokemon, and then we generate tournament data by having these Pokemon play against each other, each Pokemon corresponding to some sort of optimized AI that's trained to play as that Pokemon. Then we have different agents, we have different types of agents corresponding to the different Pokemon. We can generate a tournament between these agents, so we can collect comparisons between them. And then we can try to extract overall structure of the Pokemon game by performing this pointwise embedding. What we do when we see this, so these are the first 4 disk games, skipping the third, I'll get to the third in a second, is that the first disk game forms this really nice, clean curve that does not enclose the origin. As a result, this corresponds to essentially a transitive relationship, a hierarchy of the Pokemon. And if we color this by different attributes, so for example, if we color this by speed, we see that the speed of the agents is strongly correlated with their rating. So here, if you move from left to right, you're moving from low to high rating around this circle. And this is moving pretty clearly from slow to fast agents. So the first disk game is pulling out overall a general transitive trend associated with speed, that it's just better to be faster. The second disk game is interesting because it consists of a set of clusters. And if you color these clusters by Pokemon type, Pokemon fall into these different sort of classes, these categories. There are fire Pokemon, water Pokemon, grass Pokemon, and there are designed cyclic relationships between these types to force players to build diverse ensembles of teams when they collect the Pokemon. Right. And what we see is that these clusters correspond exactly to these different Pokemon classes. And actually, if you label the clusters by type and then sort of characterize each cluster by its centroid, reading off the performance relationships between the centroid inferred by the disk game recovers attack matrices. These are essentially design matrices that are used by Pokemon designers to actually build the Pokemon game. And so we see that this disk game is correctly recovering the class-to-class relationships between Pokemon. The fourth disk game, it does not have this sort of obvious structure that the second or the first disk game does. It just looks like sort of this like disk of points around the origin. But if you color the points by the generation in which the Pokemon were released, Pokemon have been released over time from old to new, what you see is that this is just sort of a smooth transition from old Pokemon to new Pokemon as you move radially around the cycle. What does this tell us? This tells us something interesting about the trade-off relationships between new generations of Pokemon and old generations of Pokemon, right? That each newest generation has an advantage over the preceding generation, but there's no net advantage between the most recent generation and the oldest generation of Pokemon, right? And you can think that that solves a natural design problem. As the Pokemon designer, you might want to release Pokemon that are better than the previous generation, thus motivating their use, but that don't completely usurp the balance of the game overall, right? And actually, if we color by generation inside each cluster, we see that within each of these type clusters, it's best to be newest. Right. So what's really happened, this is saying, is that the new fire Pokemon are always better than the old fire Pokemon, but the cyclic relationships between classes are updated across generation so that the overall advantage conferred by being new is only sort of local. The only advantage you get is with respect to the immediate past of Pokemon and not the overall. Right. Now, the disk game that I skipped here, the third disk game, has this structure. Again, this is in some sense, you can think of this sort of like a fat curve. It's approximately some plane curve through this space that wraps around the origin 1.5 times. Well, what is this? Again, position on this curve is closely correlated to speed. So if I plot an evaluation matrix that is a list of the agents, and here they're listed in order of speed, this is the evaluation generated by the first disk game. You can see that there's this monotonic trend. It's just better to be faster. This third disk game also generates a performance relation that's essentially a function of the agent's relative speed, but this is no longer monotonically increasing. what this really is this is a higher order correction to the first disk game. That as far as speed is concerned, the Pokemon game is approximately translationally symmetric. And the sum of these two disk games is effectively like looking at some approximation to a sine series expansion of the performance dependence on speed. And this is sort of a higher order correction. This, I would argue, is actually revealing a limitation of this pointwise approach, that it's true that these two disk games are uncorrelated, but they're clearly not independent. Position in the first disk game is predictive of position in the second game. And so this would be an example where the idea that we're looking for orthogonal embeddings with the hope that they carry independent information may fail, right? It is not true that uncorrelated means independent. And so while these examples, right, class type or generation are clearly separate dimensions of the game from this dependence on speed, there's no guarantee that all of the individual components will necessarily be individually interpretable. And that's sort of a caveat to be aware of. And you could think that this follows naturally from the idea that this is a generalization of principal component analysis, which has the same problem, where if you have data that's not sort of statistically generated in a linear fashion or Gaussian fashion, you can have nonlinear dependencies that don't get cleanly separated by principal component analysis. Now, one of the things I'll propose at the end is a way to fix this problem by thinking, instead of from the perspective of generalizing principal component analysis, from the perspective of generalizing independent component analysis, where we regularize some optimization problem with respect to mutual information between the embeddings. Okay, so as a last example, let's look at kernel BLOTTO. Now, kernel BLOTTO, this is a two-player zero-sum allocation game where I have a set of zones or battlefields, each assigns some value. There's some value for winning that battlefield. And each player has some total force or wealth to allocate. You can think maybe this is an auction model. All right, then each player receives total value equal to the sum over all zones where they allocate more force than their opponent. And then ultimately, the player who receives the most value wins the game. This is an example of a game where we have so these beautiful point clouds, but where the point clouds are really unstable. And they're really unstable because you can pick the values on the battlefields to be symmetric. And if you pick the values on the battlefields to be symmetric, then we have a whole host of symmetries within the performance relationship that leads to degeneracy within this sort of spectrum of that matrix. And that degeneracy leads to degeneracy in the embeddings. That said, if you pick the correct orientation, if you handle this degeneracy in the right way, you still end up with meaningful strategic feature extraction or trade-off extraction. So here, I won't walk through the method of coloring the points embedded in this point cloud to identify what the strategic trade-offs are. Instead, I'll just emphasize the interpretation of the trade-offs associated with each of these disk games. So the first three disk games here all have equal importance. They all correspond to a matching eigenvalue. That's where the degeneracy comes from. And they represent a set of sort of neatly interlocked cycles across the trait space, here where the trait space is the space of possible policies, that is allocations that a player can play. Now here, that space for a three-zone game is a simplex, because a player could allocate all of their wealth to one of the three battlefields, or some convex combination of their wealth across the three battlefields, or three zones. Here, if we color that space by angle within the disk game, we see that there's basically three categories here. There's a center category, a corner or a side category, and a corner category. And if you go back through the structure of the BLOTTO payout function, what you see is there's actually a nice cyclic relationship where the corners of the simplex lose to the center of the simplex, which loses to the sides of the simplex, which lose to the corners. And then these points, the center of the simplex, the sides of the simplex, and the corners of the simplex, get mapped to the extremal points on the boundary of this disk game embedding. Now, there are more equally important interlocked cycles here. For example, you could imagine allocations where you allocate most of your force or wealth to a particular zone, an intermediate amount to a secondary zone, and very little to a third zone. These are points living near a corner and near an edge of the simplex. And again, coloring by angle around this disk game, we see that there's basically three categories. Again, this is like a rock, paper, scissors cycle of some kind. This is induced by taking cyclic permutations of that sort of uneven allocation ordering. So For example, if I allocate mostly to the first zone, a little bit to the second zone, and almost none to the third zone, you can think that's like high, middle, low. Then this rock, paper, scissors cycle is a rock, paper, scissors cycle arising from the cyclic permutations of that list, high, middle, low. And it has a reflection, there's sort of a reflection symmetry here. If instead of going high, middle, low, I start low, middle, high, then the cyclic permutations of low, middle, high induce another interlocking cycle running in the reverse direction among the other three sets of points shifted down from a corner, right? And so in some ways, this is pretty nice, right? We get these strongly geometric trade-offs that are easily represented in a latent space, and have to do somewhat sort of fundamentally with the spectrum of our underlying performance function. Here, another feature that you actually see is if you look at the subsequent disk games, these patterns repeat, they just repeat on a smaller scale, right? So in some sense, there's some sort of like modal behavior going on in kernel BLOTTO. All right, now, so that's the pointwise approach, which begs a question. Can I do this exactly? Can I do this to functions? So we'd say a function admits an exact embedding if f mapping from omega cross omega to r, skew symmetric, can be expressed exactly as a sum over a finite number of disk games with some embedding maps into those disk games. And this should be true for all x, y, and omega cross omega, or at least almost all x comma y and omega cross omega. And this raises some key questions. What functions admit this type of representation, right? You can think there's a representation theory here. And if a function is embeddable in this fashion, how can we recover it? How would you actually compute this? This is where I'll go back through that list of functions I introduced in the beginning and show that all of these different classes of sort of simple functions that you can write down, all are finitely embeddable. So first, let's go back to that sine function. So suppose I had f of xy is some amplitude times sine of omega x minus y for traits drawn from the real line. Then I can always find an exact embedding of this function. You take your interval on the real line and you map it to a segment of a circle with radius square root of this amplitude, and where the number of rotations that this circle completes around the origin has to do with the size of this frequency omega. Now, what's particularly nice about this construction is if I start instead with some generic translationally symmetric function on a closed interval on the real line, I can extend that translationally symmetric function periodically and then write down a sine series for that function. Once I've expressed the function in a sine series, I can directly embed each of the terms, because each of the terms takes this form, and each of those terms gets embedded to a circle. Which means if I start with any translationally symmetric game defined on a one-dimensional trait space, at least a compact set in a one-dimensional trait space, then it's always exactly embeddable via the sine series of the function, right? Where in particular, I just take each term in the sine series and I map it to one of these circular arc segments in a disk game. And this is exactly the type of thing we were seeing in that multi-criteria example. We had this combination of circular segments. So here's a sort of a nice theorem. All translationally symmetric functions f defined over a compact one-dimensional trait space are disk game embeddable, and moreover can be embedded onto a series of circles using the terms in the sine series of the translationally symmetric function. Right, so that's fairly powerful, and we can actually generate examples where we see this. For example, if we go back to the BLOTTO example, and we really skew the weightings of the zones so that one zone is much more important than the others, then the game becomes transitive because you win by allocating more to the leading zone than your opponent. Moreover, the game is translationally symmetric because it depends only on the difference in your allocations to that leading zone. And as a result, you can break up your original simplex into essentially a coordinate system associated with how much did you allocate to the most important zone. Here, that's the zone at the top. And then in that trait space, we essentially have a one-dimensional bounded set where our function is translationally symmetric. And so the resulting disk game embeddings are a series of circles associated with the sine series of that function. That function here is a step function. And so these end up being exactly the semicircles associated with the sine series for a step, right? And you can look at the sequence of eigenvalues and they match exactly the eigenvalues associated with the sine series of a step function. Okay, so again, that's suggesting that there's a deeper functional theory here. Let's look at some other generic classes of functions. Maybe I take a quadratic performance function, right? Remember, this is all normal form games, or really finite normal form games. Or you could think about these quadratic functions as arising from Taylor series expansion of some function f that's analytic for opponents X and Y near some shared opponent Z, and this would be the second order expansion. If I write down the second order expansion, well, then f of xy is some v dot x minus y, that's your linear term, plus again, some combination of quadratic forms with respect to matrices with defined symmetries. Here, A is symmetric and B is skew symmetric. Here, you can take this whole first part and you can collapse this into a difference of ratings. This is the difference of the rating function v dot x plus 1/2 x prime a times x minus v dot y 1/2 y prime a times y. Right, so this first part, this whole component, this is perfectly transitive, Rx minus Ry, and then we've added on some component here, x prime b times y, where b is skew symmetric. This component, in a sense, is perfectly cyclic. So if you have a quadratic game, you have this nice division into components. Your first component here is transitive. The transitive component, like actually any transitive game, can be explicitly embedded in one plane by assigning the first coordinate to 1 and the second coordinate to the rating. And again, this would map all the points essentially to a curve. This would map all the points to a line in that plane where their position along the line is specified by this rating function. And so this tells me, well, all transitive functions can be embedded in this fashion. So I can take this first component and embed it by embedding onto a line. That's what we saw in the Pokemon example with the embedding corresponding to speed. And I can take the second component, the x prime b times y. This is a cyclic component. And I can embed this explicitly using the SCHUR decomposition of the matrix B. So if I take the matrix B, it's skew symmetric, I can SCHUR decompose it. The components of that SCHUR decomposition then define a linear embedding map from my original trait space into a sequence of disk games associated with projection onto pairs of the columns of this matrix Q. And so this is nice. This gives us some nice theorems, right? All transitive performance functions are explicitly disk game embeddable using a single disk game by embedding onto the line 1, the rating. And all quadratic performance functions are also disk game embedding using at most the rank of that matrix B divided by 2 plus 1 disk games. Moreover, the necessary embedding is achieved by evaluating the projection of your input coordinates onto the eigenplanes spanned by the consecutive columns of the matrix Q in that SCHUR matrix. Right, so I can do that explicitly. This is something I could do explicitly for any normal form game as long as it's finite, at least if you could churn through the linear algebra. And you could also perform explicitly for any Taylor expansion of an analytic performance function f on some small neighborhood where it's closely approximated by a quadratic expansion. Part of what is particularly nice about this approach is that the embedding map here is linear, which means that the embedding is performed by projection. And so just like PCA, I can identify feature vectors. If I look at these column vectors Q that define the projection into each eigenplane, well, these correspond to directions in my trait space. And then the trade-off represented by the corresponding disk game is just a trade-off between those axes, right? And here you can do some rotation to try to sparsify them and identify what are essentially the characteristic perturbations of the coordinates that define some rock, paper, scissors trade-off, some sort of cyclic mode in your game. Right, what I'm showing here, this is an example of doing that. This is a linear fit on a small neighborhood to data generated by some reinforcement trained agents in a laser tag environment, where they had a whole long list of traits, but the disk game embedding really boils down to only a couple of the traits. And if I pull out these sort of feature vectors Q, we see the feature vectors are strongly sparse, right? 0, essentially 1, -1, 0, 0. And so if you went back and looked at which characteristic of the laser tag agent corresponded to these different trait indices, you could identify exactly what the trade-off is represented by this game. Okay, if we can do quadratic functions, what about generic polynomials? Well, all skew symmetric polynomials take this generic form that I'd written before, where the key thing here is that this coefficient tensor C, storing the coefficients of the polynomial, is skew symmetric. As a result, I can actually write down an explicit finite disk game embedding of any finite degree polynomial in any finite dimensional vector space, really the Rn for finite n. All skew symmetric polynomials of degree n in the traits of both agent are explicitly disk game embeddable via a set of polynomial embedding maps of matching degree. If we let mat of C be the matricization of this coefficient tensor, then the matricization of C is skew symmetric because the tensor itself is skew symmetric. So I can SCHUR decompose the matricization. And then the components of that SCHUR decomposition can be used as coefficients in a polynomial, where that polynomial is a polynomial embedding function. And you can check sort of the tensor algebra here if you take a sequence of cross products of these polynomial embedding functions, you recover this original polynomial. And this, I think, like everything I've said so far suggests that this is a very generic and very expressive representation. And this polynomial argument really pushes that point, right? Because what we said is really all polynomials are disk game embeddable, regardless their degree, regardless the dimension of the underlying trait space. Which means that if I start with some other function f that maybe is not a polynomial, if it admits a polynomial approximation, call it p, such that for some choice of norm, the error between f and p is less than or equal to epsilon, then by replacing f with its polynomial approximant, I can produce a disk game embedding y such that the error in the disk game embedding is less than or equal to epsilon. Right? So the best case disk game embedding of f is better than every polynomial approximant to f, which means that disk game embedding is at least as accurate as any polynomial approximation. Right? So disk game embedding is at least as expressive as all polynomials. Right? This suggests that disk game embedding is a very expressive representation and really begs an approximation theory. Right? This is saying we can do at least as good as all polynomials. Maybe if we restrict our class of embedding functions, we can actually work out the best approximant to f using a disk game embedding. And this is what leads to, I think, really the most powerful and interesting idea in this talk, what we call functional principal trade-off analysis. So here, let's specify our objective. Let's let script y denote a finite vector space of functions that map from omega to the reals. This will constrain our space of embedding. So instead of allowing our embedding map to be anything, we'll require that our embedding map is drawn from some finite dimensional vector space of functions. This could be polynomials of some fixed upper degree, maybe Fourier series with finitely many terms. Pick your favorite function space. Now, note, I say pick your favorite function space. There are strategic choices of function spaces, and this gets to some of the deeper and more nuanced ideas here. Different classes of games are better suited by different function spaces. So for example, finite extensive form games, in some sense, fundamentally are high order polynomials. They're really high order multilinear functions, which means that piecewise polynomials form a pretty compelling basis, and you can try to truncate your polynomial basis using things like Monte Carlo tree search to adaptively pick the terms that you use in your polynomial expansion. In contrast, translationally symmetric games, like that BLOTTO example we'd seen, are much better expressed by a function basis that reflects the symmetry of the game, in this case, Fourier series. And there's different sort of considerations you can make to guide your choice of function basis. Then we'll try to introduce an embedding map, that is a mapping y from omega to R2D, constrained to live in this space. And we'll try to pick the best embedding map from this space in the sense that it will minimize some square error between my true performance function and its approximation using the disk game. So recalling that we're thinking sort of things in an empirical sense, let's imagine that we're sampling agents from some distribution pi, and then we'll seek an embedding y that minimizes the discrepancy between f and the disk game approximation of f using the embedding map y in this square norm sense, where this is the expected discrepancy squared when I sample agents randomly from my population. And we'll constrain our embedding to consist of embedding maps drawn from a chosen function space, where we'll require that they're all orthogonal to one another, right? This is enforcing that, or sort of independence via uncorrelated embeddings. It turns out there's a very clean closed form solution for this, which maybe is not surprising to you if you were thinking about the analogy to reproducing kernel Hilbert spaces. Given pi and given omega, we can define a Hilbert space for functions over omega. Right, so I can define an inner product. The inner product between g and h with respect to pi is the integral of g complex conjugate times h with respect to the measure pi, and I can induce an associated norm. And then I'll consider functions that have finite sort of L2 norm with respect to this inner product. I can then define an integral operator, capital F of pi acting on g, to be the integral over all y of little f of x comma y. So I'm thinking of little f like a kernel for this integral transform, times g of y, pi of y. This integral operator is the analogy in the functional setting to the performance matrices I was using in the discrete pointwise setting. Now, provided my function little f has finite norm, so is sort of square integrable with respect to the measure, has finite variance when you select an agent in random, then the imaginary number times this operator is a Hilbert-Schmidt operator. which means it admits eigenfunctions. We can have eigenpairs like phi and lambda, and these eigenfunctions have really nice properties. They're purely imaginary. They come in complex conjugate pairs. You can order them from largest to smallest. And moreover, we can guarantee that this integral operator admits a possibly infinite sequence of eigenpairs where I can express the kernel almost everywhere as a linear combination of outer products of the eigenfunctions. This means that I can take my kernel and I can express it as a sum of outer products, and I can rearrange that sum of outer products. This is essentially your eigenvalue expansion of the kernel. And I can replace the eigenvalue expansion of the kernel with the equivalent SCHUR real form of the kernel. And doing that gives me exactly the embedding functions that I would like. So what's our solution? Given our original problem, so that's some performance relation or payout function over omega, a distribution of agents over omega, and a particular function space, finite dimensional, then first project F onto the set of all outer products of basis functions for your function space, where here you can choose these to be orthonormal via some sort of orthonormalization procedure. So we project F onto the span of this space. This is like script Y cross script Y. Then the projected function F is degenerate. It has a degenerate kernel. It can be expressed as a finite combination of separable functions. So we can eigendecompose it. We can compute that sequence of eigenfunctions and eigenvalues. And then I can assign my embedding functions to be square root of 2 times the magnitude of an eigenvalue times the real part of one of the eigenfunctions and the imaginary part of one of the eigenfunctions. And this exactly solves this optimization problem. Right? And you can think there's a deep analogy and sort of synchrony here to the type of solution that you would be using in the pointwise setting if you restricted yourself to a finite dimensional vector space of linear embedding maps. All right, and this really introduces sort of a universal approximation theory for this approach. We can now define our space of embeddable functions. All linear combinations of finitely many separable functions, where a separable function is expressed as an outer product, is a disk game embeddable function. And all finitely disk game embeddable functions are represented as a linear combination of separable functions. It means that the space of finitely disk game embeddable functions is exactly the span of separable functions. It's the space of degenerate kernels. Then, moreover, any function square integrable can be approximated to arbitrary accuracy via some linear combination of a sequence of separable functions, because that sequence of eigenfunctions converges to the kernel almost everywhere. Which means that this functional approach is at least as accurate as any standard approximation scheme where you approximate a function to multiple variables via a sequence of separable functions. Right? So polynomials, Fourier series, whatever, that if you pick an appropriately expressive basis, there always exists an embedding map which will achieve at least the error associated with any standard function approximation scheme. Okay, so we can go through some more properties here. These all follow naturally sort of from your standard Hilbert-Schmidt type statements. So we can guarantee existence for certain classes of functions, in particular square integrable functions. Uniqueness follows provided the eigenvalues are distinct. And this follows from requiring that the embeddings are orthogonal. We can evaluate the importance of the embeddings via the size of the corresponding eigenvalues. If we use the eigenfunctions are mutually orthogonal. This follows some symmetries of the function f. And just like what we saw in the discrete case, in the finite case, we get low rank optimality, where if we truncate our sequence of embeddings at d embeddings, we get the best approximation to the original function f using sort of a square norm error, right? Measuring error in terms of variance. Okay, so what I'd like to conclude with here is just one last example of doing this in a functional sense. So here, this is again a simplified example to make the story clean. We'll imagine that we're considering some simplified poker game. This is KUHN poker. I have an N card deck, single card hands, 2 players, a single betting round, and fixed betting sizes. And this gives sort of a small game tree. This is essentially a shallow, extensive form game where everything interesting arises from the fact that we have incomplete information. Now, here, the experiment we'll perform this functional principal trade-off analysis analytically on the game. This is a small enough game that you can do things explicitly. And we'll also do it empirically by sampling a series of trained agents and comparing the identified trade-offs coming from an empirical approximation of the functional approach. I won't talk through the exact experimental procedure here for the sake of time. Let me just show you the results. The results are that these two approaches essentially match. The empirical approach can recover the exact functional approach, and you can study the convergence rate in like sampling limits. But moreover, the trade-offs discovered are intuitive and sort of strongly descriptive of the underlying game. In particular, the first disc game is a trade-off associated with incomplete information on the bet cast by the first agent. So the first player can choose to bet. That bet could be honest or dishonest. The second player then needs to infer whether to call by guessing whether the first bet was honest or dishonest. If they guess correctly, they have an advantage. If they guess incorrectly, they have a disadvantage. And so we get a 4-point cycle between the first agent lying, the second agent guessing that they lied, the first agent telling the truth, the second agent guessing that they told the truth, and the first agent lying. And then we get a second cycle associated with the bet cast by the second player, where again, if the second player lies and the first player guesses that they lied, then the first player has an advantage. But if the second player actually told the truth, then the first player has a disadvantage, and so on. And so we get this really clean pair of trade-offs that are directly related to the fundamental pair of incomplete information trade-offs or strategic dilemmas in the game, right? Should you bluff or not when you bet? And when you see a bet, was it a bluff or was it the truth? Okay, so I think here, for the sake of time, I won't go through these last empirical slides. These are really just pointer slides to say that there's a lot more analysis that you can run once you recognize this functional theory. The fact that it's tied to sort of this Hilbert-Schmidt type theory really allows you to do a number of powerful things because there's a lot known about eigenfunctions of kernels. Right, so we can get sufficient like sampling criteria, all sorts of different criteria that control the empirical application of this method. What I'd like to conclude with is just some different ideas to show you how we're extending this work. So one idea is to look at sort of perturbation bounds on Monte Carlo estimates to performing these functional embeddings, and try to tighten sufficient sampling bounds by looking at different concentration bounds, different tail bounds. You can also think about adaptive sampling techniques where you iteratively pick your agents and pick the comparisons you make in order to reduce the uncertainty in this embedding as quickly as possible. And there's different ways of doing that. It's like a Bayesian optimization problem. You can think there's different guidelines for choosing your basis function. So one avenue of research is to ask, should I use Fourier bases, polynomial bases, wavelet bases, piecewise polynomial, maybe some Gaussian field, right? There's all sorts of different classical function spaces that we could be working with. Which is the best? Well, it depends on your game, and we've done some work to try to predict that. In particular, the choice of basis function matters if we try to tame the curse of dimensionality, right? What's often true in these games is that these functions are, in some sense, simple functions in very high dimension. And so what we need are good, clever, structurally inspired sampling techniques to correctly pick a sufficiently expressive and sufficiently concise basis. Right? And there's different ways of doing this. You can try to use some sort of autoencoder or inspire your basis using sample runs through the game with something like Monte Carlo tree search. And we have other sort of questions here. We could try to learn embeddings using other types of function spaces. So maybe function spaces parameterized by different neural networks. We can look at other regularization terms, or terms that promote statistical independence instead of uncorrelation. This is like trying to do independent trade-off analysis or functional independent trade-off analysis. You could try to do TDA on these shapes, right? You think that this whole thing is transferring strategic structure of a function into geometry. If you want to describe the topology of some set in a high dimensional space or a medium dimensional space, well, then maybe you'd like to use TDA and think about some invariances of that space. And there's ways of interpreting those invariances. And then last, and I think most excitingly, is once you have this tool for visualizing agents and visualizing a meaningful latent space, we can use it to say things about learning and selection dynamics. And so there are deep connections here between this particular way of embedding a function and self-play dynamics, adaptive dynamics, continuous best response dynamics, replicator dynamics, and so on. And this is really an active and sort of exciting area of research. So with that, I'd like to conclude the talk. What we've shown is that an extremely wide class of functions admit this representation, that we can recover approximations to idealized embeddings from empirical data, that we can control that approximation theory, and we can then mine the geometry of those maps for strategic information about the original game. So with that, thank you for your attention, and I'd open the floor to questions.
Awesome. Thank you so much, Alex. Okay, folks, so we got started a few minutes late, excuse me. So I think we have time for